Hi everyone, this is Paul Carter Brown, coming to you from Johannesburg, South Africa. It's Sunday afternoon, 26th of July. I hope everyone is staying safe in these trying times that we're living in. So, quick video blog. I came across a blog by Graham Rocha on from the Micronaut team. In fact, he started Micronaut as well as being the key guy behind the Grails framework. And I'm a bit of a performance junkie. I love doing stress testing, throughput testing. I'm actually the director of a software fintech company in South Africa, and I've been in the IT space for about 25 years, everything from working on IBM mainframes back in the day to a number of years of C++ programming, and then about 20 years of experience in Java. Um, Starting from Sun Application Server all the way through to Glassfish, JBoss, Tomcat, Tommy, Wildfly, a bit of Micronaut, Quarkus, um, uh, Spring Boot, you name it. I've looked at a lot of platforms, worked with a lot of them, and I came across Graham's blog where he was looking at some of the differences between performance, startup time, throughput, memory utilization of Micronaut 2 versus Quarkus 131 and Spring Boot. I thought it was a great blog, very interesting. Lots of good stats coming out of it. And when I watched it, actually, it was only a few days ago that I came across it, and I saw that obviously, Quarkus has moved on a bit. Micronaut, I think at this time it was milestone 2. It's now on release 2, and JDK 14.02 just came out recently. So being interested in this kind of thing, I thought it would be a good idea to run through some of Graham's results, see if I get similar results, and have a bit of a look at what's going on behind the scenes, trying to see if I could understand you know, just get some insights from the results. So just a bit of prior disclosure, I don't work or have any affiliation with Red Hat or Micronaut. I have been on projects where Micronaut has been used. Internally on our projects, we actually use Quarkus. Prior to that, did a lot of work in the telecom sector, building real-time charging systems. That was actually on top of Tommy. We utilize these tools on a day-to-day basis, but I'm not affiliated with either Micronaut or Quarkus. And although I tend to use Quarkus more, I want to come across as being as open-minded on both platforms as possible. And it's an interesting just looking at the different approaches of the platforms, and I'm just going to comment from what I can see, the observations that I can make. If the guys from Micronaut or Quarkus want to comment on some of the observations I found, they're free to do so. But really, this is a bit of shooting the breeze, having a look at the differences, and allowing everyone to make up their mind in terms of what the major differences are between the platforms in terms of performance. So in this analysis, I'm going to focus on more sort of the runtime, memory, and throughput of the two platforms. Graham's analysis actually included Spring Boot. It was quite far behind the others in pretty much everything other than compile time, because it doesn't do any ahead of time compilation. So I'm just going to focus on the sort of more micro platforms, being Quarkus and Micronaut, and leave Spring Boot out of this. And I'm not really going to get into differences in terms of time to first response and compile times and startup times. I mean, you'll be able to see the startup times when I start the containers, But really, this is more looking at runtime. What is the memory profiling, memory utilization, threading models, and throughput that one can get on both of these containers. So let's jump into it. So what I've done is just a bit of info on my system. So I'm running Linux Mint 2004, running an i7 2.6 gigahertz, 6 cores, 2 threads per core. So that's basically 12 hardware threads, 32 gigs of RAM. So that's my system. It's a Dell XPS 15. So let's have a look at the two projects. So what I've done is I've downloaded the test projects that Graham had, the Micronaut one and the Quarkus one, and I've gone through the POMs and just updated to the latest versions. So on Quarkus I've updated to 1.6.1 final, which is the latest release version, and then on Micronaut I've updated to 2.0.0 across the board wherever I basically did a find replace for milestone 2 to just use 2.0.0. There are a few other changes I've made in the code which just allow me to pass in parameters in the query strings for things like it's basically a greeting service where you pass in a request with a name and it responds back with hello and then the name that you passed in. I've added in another parameter or two to allow you to simulate some different scenarios, but I'll show that later. And then the other key thing is just on the Micronaut side, I set it up to listen on port 8081 as opposed to 8080. So just to speed up the testing, what I've done is I've got it so that Quarkus listens on port 8080, Micronaut on 8081, so I can run both of them at the same time, and then run load tests against each of them without having to start one and stop the other, etc. I then have a a script here, and I'll put all of this on GitHub and put a link to it so that people can run it themselves. But it's just a simple bash script which makes it a lot easier for me to run scenarios across the two platforms. I pass in a few parameters, so the concurrency of the load test, sleep, which I will get into a bit later, the starting heap size, the maximum heap size, what JVM to use, because I actually did some tests between both the hotspot and OpenJ9 JVMs, got some interesting results with both of those, and then a mode which I will also discuss a bit later. And basically what the script does is it kicks off both Micronaut and Quarkus. It then gets their process IDs, puts in a trap so that when I shut down the script it'll also kill both of the app servers. And then I run a watch command here which does a few things. It prints out some info of the test it's running. It runs Apache Bench, pretty much the same settings as in Graham's tests, with keep alive, a concurrency. I've got it here to set a time of 3 seconds, so it'll run a load test for 3 seconds. This is just a very high number of iterations. It'll never get to that. It'll just end after 3 seconds. It then calls into the endpoint it's testing against. The sleep thing I will discuss later. It then just greps the requests per second. Then it runs a PS to show the resident set size of the memory, utilization of the JVM, and the number of lightweight processors, which is effectively the number of threads that the JVM is using. And then what I've also got is, you see that when I start up the JVMs, I've got native memory tracking on just at summary level. It doesn't have a big impact on performance. But what it allows me to do is to then run a JCMD command to show the native memory stats, and I'm again grepping, and what I'm showing here is the heap utilization, class utilization, thread utilization, code, and other. So these are parts of the native memory utilization. Lots of people focusing on heap, but when you're looking at RSS, Heap is part of it. It's mainly these other areas here that also come into things. There are other parts of native memory utilization, from the garbage collector and JIT caching and that sort of thing. But when I looked at the native memory utilization of the two platforms, those were pretty similar. I really just wanted to show heap, class, thread code, and other memory utilization. These are the ones where I've noticed a bit of a difference in the utilization of the two platforms. So that's it. So this script runs. It will, as I say, kick off both JVMs. Then it'll run a 3-second load test against Micronaut, then print the memory results, then run a 3-second load test against Quarkus, print the memory results, and then carry on back and continue doing that. So, when you run the tests, you'll see it updates about every 6 seconds, shows the results of the last test, and then obviously the JIT compiler kicks in and you start to get better performance, and then things kind of stabilize at a point. And that's really where you want to take a look and say, okay, what are each of the platforms doing? What is their transactions per second, and what is their memory looking like? So that's what I'm going to be doing. So it allows me to pass in a few different parameters and see the results of what the two different platforms are doing in terms of memory utilization and throughput, which is what I want to focus on here. So what I'm going to do is start off with running the script with 20 a concurrency of 20. So that's effectively as though there are 20 threads hitting the each of the JVMs. I've got 0 here, which I will explain later. It doesn't really do anything right now by setting it to 0. This is the heap starting size, and then the max heap size, which I've got the max at 128 megs. Then this is the virtual machine version I want to use. I'm using hotspot here. And then this last parameter is kind of impacting the exactly what's going on in each of the platforms. DE stands for default. So what I've done here is this test is going to run a concurrency of 20, max heap size of 128 megs, hotspot JVM, and then default settings, i.e. on Micronaut and Quarkus, it's going to run pretty much exactly the same as in Graham's tests that he had run, where the platforms are just running in their own default modes, and without any tuning or changes or anything like that. So I'll kick this off. You'll see it firstly it just sets and makes sure we're running for Geno 2 hotspot. Then you can see it started up the two containers. They both start up in pretty much the same time. And now we're starting to see some of the results coming through. So what's best to do is to wait a bit for the JIT compilers and things to stabilize and start to see what sort of transactions per second we're getting, and what the memory is looking like. So let's have a look here. So as it says, we've got a concurrency of 20, 0 millisecond thread blocking. I'll show you what that does later, but effectively with 0 milliseconds, it's acting pretty much the same as the tests Graham had done. Thread mode is default. So requests per second, we're looking at so Micronaut is always on the top, and then Quarkus below. Micronaut, we've got 80 odd thousand, I'd say around 85,000 requests per second coming through. The RSS about 267 meg. On Quarkus, I would say what's this, about 12 or so percent slower in terms of requests per second, around 74,000 requests per second. RSS is 268, so here we've got the RSS is pretty much identical between the two, interestingly enough. And then this is just a breakdown of the memory. If we see here, the heap on Quarkus is sitting at what the max allowed was, so it's um, ended up um, committing the entire heap into as part of RSS, whereas on the Micronaut side, it is used. The heap has actually only grown to about 71, 72 megs. Um, then the thread, the memory usage of threads in the native memory is a bit higher in Micronaut than in Quarkus. Code a bit lower in Quarkus than Micronaut. Um, Sorry, I've got it wrong. So this is the class memory is higher on Micronaut than Quarkus. The thread memory higher on Micronaut than Quarkus. The code memory is pretty similar between the two. And then this other, which there's not too much information on it. It basically, if you do some research, it says that other is everything else that's not covered in other in any of the other categories. And I'll show you some interesting observations are made in terms of this other memory usage. But as these two platforms run here, you can see. So right now the Quarkus RSS is around 280 compared to 270 on Micronaut. So Quarkus is using a bit more memory, about 10 megs more, and that 10 megs is mainly coming from the heap, more heap being used. And this isn't, the usage within the heap itself. It's actually the total heap size. So because we've specified on each of these that the starting memory can be 0 and it can grow to a max heap size of 128, we can see that Quarkus has, upon booting, it's grown its heap to all that it can, and now it's using obviously part of that, and the garbage collector is then collecting and freeing up memory within the heap. But the difference is quite interesting here about how Micronaut, when it boots up, its heap doesn't grow that much compared to Quarkus. However, this other memory is a lot higher on Micronaut than Quarkus. So here on Micronaut it's about 16 megs, Quarkus about 3 megs. And as things continue running here, we can actually see the difference in requests per second around 10,000, and Quarkus using right now about 20 megs more in RSS than Micronaut. So this here, as I said, it's a test which is pretty similar to Graham's main test, running 128 meg heap, max heap, and then comparing throughput and memory. And I concur completely that in this test, Micronaut is doing higher requests per second and utilizing a lower RSS. Not nearly to the extent of what was observed in Graham's results. I think this is probably due to some of the changes in Quarkus from version 1.3 all the way up to version 1.6. So in 1.6 you can see that the difference isn't quite as big, 270 odd versus right now Quarkus sitting around 300. Okay, so that's kind of my baseline, and what I'm going to do now is have a look at some changes and differences in the platform. So what I'm going to do is, while this is running, I'm just going to kick off Visual VM and have a look at what's going on inside each of these containers. So you can open Micronaut and Quarkus, and what I want to show you here is if we just go to monitor on each. So interestingly enough, so live threads here on Micronaut around 45, Quarkus 47, so not much of a difference there. Let's have a look at the threads here, see what threads are doing. So what we can see here is, if you look at the threads that are running, and let's just pick up one of these event loop threads when it's actually busy running and doing something. So here's one report running. So this stack trace here is showing you what's happening in one of these threads that's actually runnable. And you can see that the threads that are busy is pretty much all of these new IO event loop threads. Okay, and there are 25 of them. So 25 threads all processing this incoming traffic. Let's have a look at the Quarkus side, see what's going on here with threads. And this is where things get a bit interesting. So what you can see here on Quarkus is we've got some pretty busy threads here, all these vertex event loops. So this is the Quarkus's event loops. Here we can see that there are 12 of them. Quarkus has one per hardware thread, so it's got 12 of them running. And then we can also see that there's an executor pool here. So an executor pool right now, it's got 24 threads in them. They're busy now and then. And what's actually happening here in Quarkus is that the default sort of mode of Quarkus is that it uses Vertex under the hood. Vertex is accepting these requests and then handing them over to an executor pool, so that one's actual code and business logic, in this case it's some REST services. So the thing that is, getting your greeting, concatenating the two strings together and doing all of that processing has actually been handed over to an executor pool. So there's this handover context switch happening from your event loop to an executor pool, which then responds back to the calling client. So what this means really is that for every request coming into Quarkus, it's being accepted in an event loop thread. There's a context switch over to an executor thread, does the processing, and then sends the result back to the caller. So that's actually quite a big difference between the two, is that Micronaut is not using a separate thread worker thread pool, it's using its event loop threads. And what I picked up on that, interestingly enough, and I'll just jump over to my browser here, is this is a Micronaut article, so publication from this year, just it's titled Don't Let Event Loops Own You. And what's interesting, if I just go down here, is that in Micronaut prior to version 2, it would excuse me, it would by default do the same thing that Quarkus does, which is to accept work with the event loop, hand the work over to an executor pool, which would then actually process the result with the code written by the container user. And that was it had some different modes, but the default mode was effectively that it would utilize, if you were returning a non-reactive data type, so if you're returning, like in this case, a plain string, the work would be done by an executor pool, and there would be the context switch happening. In Micronaut 2, they changed that to default to no matter what type you're returning, whether you're returning a reactive type or a plain Java type like a string or anything like that, it will always use the event loop. It will not do a handover to an executor pool. And that's what we're observing here in Visual VM. As you can see that the event loops are doing all of the work. There's no handover happening. But that comes with a bit of a caveat, and that if you, and I mean it specifies it pretty obviously in the documents here, is that the rule with event loops is do not block. And that's key, because if you've got an event loop which is now running user code and is blocking, and that could be waiting, let's say you do a call to a database and you're then waiting for the response, or even if you're doing some pretty intensive calculations or something like that, effectively you're saying that this thread is now no longer available for the platform itself to do accept new connections and accept incoming data coming in on the TCP socket. So the entire platform becomes pretty hamstrung if you end up using its event loop threads for business logic and blocking and that kind of thing. So what that means, and I'm just going to show you a quick example here, is if I stop this quickly, so let's just see where we're sitting here. So we're now sitting about 89 or 90,000 requests per second on Micronaut, 75 odd thousand. The heaps have changed a bit, maybe just because I started up Visual VM, so let's not look into that too much. Our observations pretty much do show that under these conditions Micronaut does use a smaller heap. Right now it's not showing that, but let's not let that cloud our judgment. I have noticed Micronaut being lower under these test conditions. So let me just stop this test and jump over and just show you some changes that I've done to the code on Graham's test. So excuse me, what I've done is in the service of each of these projects is I've just threading through a long, being a sleep time, and just a little try catch telling the thread to sleep for that amount of time. So if you pass in on the resource itself, passing in a sleep as a query parameter, it threads that through, and the thread, when it's processing in the service, it'll then sleep for that amount of time. In the test that I ran now, I did it with passed in 0, which means it won't sleep at all, which is kind of the control. But we can pass in different values here to get the thread to sleep and basically simulate one doing a bit of database work or calling off to a remote system. Anything where you end up doing a bit of work in your business logic code, it's kind of simulating that of using the thread so that it's not available to the container. Now, people could argue and say, look, you should never really be doing any blocking. You should be using reactive database drivers, and these sorts of things are becoming a lot more commonplace. There's a lot of work. There's reactive hibernators is coming out, or is out, I think, already. So it is possible to write completely non-blocking code, but I think its key is that, practically speaking, people aren't really embracing that to the full extent that it can, because things get pretty complicated. If you wanted to write code which does 20 or so different database calls and updates and deletes within the context of a transaction, and you try and do all of that in a completely non-blocking manner, it's a new paradigm. A lot of developers aren't used to it. They make mistakes. They won't know what to do. And really, it's a lot simpler for people just to do non-reactive standard type coding, where you will call your database, do a query or an update, wait for the results, and then continue processing. That ends up blocking, but it is, I would say, still the norm in terms of how people write code. And because of that, I just want to show that if you were to end up just writing normal blocking type code, calling a database or whatever, that's the scenario I'm trying to simulate here. So what I'm going to do now is pass in a sleep value of, instead of 0, let's pass in a sleep of, say, 5 milliseconds, and just to see how the results vary a bit. So let's just wait for the test to kick off. Right, so tests are warming up. Let's wait a little while and see what the throughput sits at. So obviously the throughput is going to be a lot lower now because the threads are sleeping, but they're pretty similar. Not a big difference between them. If you remember earlier, we saw that Micronaut uses 25 event loop threads. So this is with a concurrency of 20. We're pretty much getting each thread accepts a request, sleeps for 5 milliseconds, and responds. And that's pretty much what's driving the response per second. Let's now do this, and let's put it up to a concurrency of 200 and see what happens. So now we've got a lot more requests coming in. Concurrency in terms of concurrency than the size of the thread pool available in Micronaut. So Micronaut had a thread pool of 25 event loop threads. We're now getting each of those to sleep for 5 seconds, simulating some database work or something like that. And straight away you can see this huge difference that's cropped up. So what's happening is, and we can observe it in Visual VM. Let's just have a look at Micronaut and Quarkus again. So in Micronaut, the threads end up sleeping on the event loop threads, and there are only 25 of them, so you end up with this backlog of work queuing up, waiting for this thread pool of 25 threads, because we've got sort of concurrency of 200 coming in, only 25 threads available. So things queue up, and the result is that we start getting this dramatic decrease in throughput. If we compare that to the Quarkus side of things, what we've got here is an executor pool that's grown up to 200 threads. So it's got a thread per request coming in, and the event loops are now handing over to the executor pools. The executor pools are the ones that are actually doing this background work, in this case this blocking calling, simulated with the thread sleeping. And because we've got a much higher number of threads in this executor pool, we've ended up with a result of, what's that, about 8 or so times higher throughput on Quarkus than Micronaut. So what we've kind of purposefully engineered here is a scenario where we are playing to Micronaut's weakness, in that it is using the event loop for the actual business processing. So we're doing what Micronaut clearly doesn't want you to do. We're blocking in the event loop. You do not want to do that, and this is why you don't want to do that, because of this dramatic increase that you have in throughput by keeping all of the event loop threads working on blocking calls. So what I want to do now is, because we've seen that there's this big difference in approach, the sort of default out of the box approach. So we've got Micronaut using event loop threads, Quarkus using a worker pool, and that's a very different approach by default, in that Micronaut's default approach used to be the same as what Quarkus's was. It's not now. But let's level the playing field and say, let's make Quarkus act in the same way as Micronaut. So I'm going to I'm going to show you a change in Quarkus, where I've created what's called a reactive route. It's a REST endpoint which utilizes the event loop threads as opposed to handing over to a worker pool. So I'm just going to stop this and just show you the code for that. So on our message resource here, this is the code. So this is a REST endpoint. Instead of hello and then name, it's hello2, and a slightly different syntax here for specifying your path parameters. I'm still pulling in the sleep query parameter, but what this is using is, it's using the vertex routing, which does not hand over to REST Easy and the REST Easy worker pool. It's just using vertex to process the REST endpoint, and is not handing over and doing a context switch from the event loop pool to a worker pool. So if I end up changing my load test, instead of calling hello but to call hello2, then it's going to behave in the same way as Micronaut, i.e. everything will happen on the event loop thread. And my little monitor script changes that by, if I have mode here and I pass in EL, which stands for event loop, then it'll end up calling the hello2 path on the on Quarkus, i.e. level the playing fields, Quarkus, Micronaut, both using event loop threads. So let's kick off our test like that. I'm going to change back to a 0 sleep time, 20 threads, 128 meg heap, still with hotspots, and I'm going to say EL. So what this is exactly the same as the original test with concurrency of 20, no sleeping, so no blocking whatsoever, and both platforms now using event loop thread pool for all of the processing. And let's kick this off and look at the results. While that's running, I will just jump off to Visual VM quickly and have a look, and just let's have a look at Quarkus and look at the threads. And what we see here is that there's no executor thread pool threads here. There's one which I think is just the default it starts with. It has at least one of them running in the pool. But all of the work now is happening with these vertex event loop threads. So we've done what we intended, is to say let's make sure that just the same as Micronaut, everything is happening on the event loop threads. And let's have a look at our results. So interesting, we've got about 88 odd thousand requests per second, so Micronaut acting the same as it was before, but now we can see on Quarkus the throughput has increased dramatically. We're sitting around 126,000 requests per second, and interestingly enough, because of the not having this executor thread pool and all of the context that is utilized by threads not only in the heap but also in your native memory, we can see that also the result is that the Quarkus RSS is now lower than the Micronaut RSS. So Micronaut memory utilization is higher, Micronaut throughput is lower, and you can see the big difference here is immediately is that, unlike before, when Quarkus has started, it hasn't ended up using the full 128 megs of heap that it could grow into. It hasn't grown that. It saved some RSS because of that and ended up with a slightly lower memory. I'm sure as we wait here, these memory differences, I mean, there you just saw a jump there, Micronaut up to 244, Quarkus still sitting around 208. But the biggest difference that we want to observe here is that when we level the playing fields, the Quarkus throughput, by not handing over to an executor pool, is a lot higher than Micronaut. Just to show you again, so let's just kill this test, go back to defaults. So only difference here, now I'm going back to the Quarkus handing over to its worker pool, and we want to simulate and see we get back to what we did before, where now Quarkus is using higher memory and getting lower throughput than Micronaut. If we just wait for it to stabilize. So there's our sort of difference of about 10,000 requests per second, so Micronaut faster than Quarkus in this case. But as I say, the reason being is it's not really apples for apples comparison. It's Micronaut being optimized, doing everything on the event loop, but at the expense of, as I say, if I change and do some blocking calls here, it's at the expense of its ability to scale with doing real sort of blocking work, calling databases, that sort of thing, is where we start getting this big difference, because we would be, in this case, we playing into the weakness of using your event loop for everything. Okay,
So, summary on that: apples for apples, level playing fields, both using event loops. Quarkus ends up with lower RSS and higher throughput. Um, Now, what I want to do is just some interesting tests around that. Is I don't believe that running an event loop for your processing is really the norm. What I'm going to do now is change to a mode where both of the containers end up using a handover to a worker pool, and that is achieved on Micronaut by setting the thread selection to IO. And what that does is it makes it pretty much do the same thing as Quarkus. That's described in the documentation. Is that in Micronaut 2 you can go and specify that you want to use IO, and then it'll be executed in an IO dedicated executor pool. So if I pass in IO over here, then again now it's an apples for apples comparison with both containers utilizing an executor pool for their work. So if I run now 200 threads, 200 concurrency, let's change to a 0 millisecond blocking time. So it's a non-blocking concurrency of 200, both of them apples for apples handing over to a executor pool. Let's look at Visual VM again. So if we go to Micronaut, we will see now that Micronaut is now using this fork join pool for doing the actual processing of the business logic as well as the event loops. So now we're seeing exactly the same behavior between Quarkus and Micronaut. Both of them have the event loop thread accepting requests, etc., but then handing over to worker threads. So we're doing an apples for apples here, and let's compare. So what we can see here is that the in this case Quarkus's throughput is higher than Micronaut by about, in this case, 10,000 requests per second. The memory, Quarkus is using more RSS than Micronaut. If we have a look at the breakdown, you can see it's because of this high utilization on the heap, and whereas on Micronaut it's got a bit of a higher utilization in this other section, but a much lower utilization of the heap. The heap just hasn't grown to 128 like it has in Quarkus. So Quarkus is a bit faster, and Micronaut using a bit less memory. Now I'm just going to play around with some scenarios here. Let's just kill this, and what I want to do is let's just put in a 5 millisecond blocking on both scenarios and see what impact that has. So now we end up with, I think we're probably going to see, I mean, most of the time now is pretty much these two containers, threads are sleeping, so we're going to end up with them sleeping most of the time. I don't think we're going to see a big difference in throughput. And from a memory perspective, we can see that Quarkus is using quite a lot more RSS than Micronaut. So Micronaut about 290 megs, Quarkus 350 odd megs. So a fairly large difference there. And if we look at the difference again, it's because Quarkus has grown its heap, its maximum heap, all the way up to the max allowed, 128 megs. Whereas Micronauts is a lot more frugal on the heap. It just hasn't grown its heap to that extent. And on the other memory, again, we're seeing this quite a big difference. Micronaut using more in the other part of the native memory than Quarkus. Things stabilize now. Throughput pretty much the same. 294 megs versus 362, so quite a bit more RSS utilization on the Quarkus side. I'm going to now run the same test, but I'm going to jump over, instead of using the hotspot JVM, I'm going to use OpenJ9. Now OpenJ9 is a lot more frugal on memory. Oops, sorry, I can't do that. So OpenJ9 doesn't let you specify a starting heap of 0 megs. I just need to specify 1. Let's just wait for the results here. So I don't know if you've used OpenJ9, guys. It's a lot more aggressive on claiming back memory. It doesn't support the native memory tracking like the hotspot JVM. Maybe it's got an alternative. I haven't looked, but so I'm not. It's not showing a breakdown of the native memory. But what it is doing is it's a lot more aggressive in reclaiming unused heap and memory that was reserved but not committed. It ends up being claimed back and given back to the operating system. So you can see that the RSS actually jumps around a lot more and is generally quite a bit lower than it is with the hotspot JVM. And here we can see things stabilize. Throughput is pretty much the same because most of the time it's just sleeping anyway. And the heap is going up, or the RSS is going up and down on both of them. But we can see that, they sort of one. So right now we've got Quarkus on 200 odd megs, Micronaut on 180 odd megs, Micronaut 192 versus 204. They jump up and down a bit, but there's not a huge difference between the two. So right now it's sitting around Quarkus being around 10 megs more or so. There's a bit of big difference, like 17 odd megs, 18, 19 megs difference. And so we go. So just an interesting observation. I'm not going to do a lot with the J9 JVM. Just interesting if you want to save memory and costs in your cloud environment, definitely have a look at OpenJ9. Its throughput's going to be a little bit lower. I can show you if I just quickly do a test here with 0 sleep time. So let's just get some raw throughput going on both of these containers, see what happens. I observe that OpenJ9 is a few percent, maybe 5%, depends on what kind of workload. Some people say up to 20%, but it is a bit slower than Hotspot, but its memory utilization is quite a bit lower. So let's just wait for this to stabilize a bit. So you see here, our RSSs are pretty low because without us sleeping, the thread pools end up being a lot lower. So now we've got like 131 threads on Quarkus, 126 on Micronaut. The memory in this case, we've got Micronaut a bit higher than Quarkus, and we've got still pretty decent throughput in terms of requests per second on both of them. So there's so both of them come down. Micronaut 175, Quarkus 170. Okay. So let's jump back to hotspots. It's the more typical JVM that people use, and let's I'm going to show you some interesting observations I picked up. So this is kind of back to apples for apples, both using a handover from event loop to a worker pool, concurrency of 20. But what I'm going to do now is just in terms of this test, we've run this scenario a few times, and we observed that Quarkus was using a slightly higher RSS than Micronaut because of this initial heap size being quite a bit bigger than Micronauts. And I happened to kind of by mistake come across a bit of an interesting observation. So let me show you here. So let's just wait. So interestingly, right now Quarkus is a bit lower than Micronaut, but I'm sure Quarkus will go up soon enough. I have noticed that when things stabilize under these conditions, it ends up with Micronaut using a bit less memory than Quarkus. Um, but anyway, let me show you something interesting. Is if I go here and change the maximum heap to something like 20 megs as an example. Okay. Um, both of the containers boot fine. They're happy enough. Obviously, there's going to be a lot of garbage collecting going on. But what I've noticed is that this then plays into Quarkus, and that it can't now go and allocate this large initial heap. It can only allocate up to 20, and it ends up with Quarkus using significantly less RSS than Micronaut. So at 128 meg max heap, Quarkus boots up, grows the committed memory to 128 megs. The heap then doesn't come down much. It's kind of using the memory within the heap and garbage collecting, but you end up with the larger RSS. If, however, you drop the maximum allowed heap to 20 megs, now Quarkus is using, in this case, about 35 megs less um, than Micronaut in terms of throughput. Obviously, there's high garbage collection overhead, so throughput is pretty similar. Quarkus is a slight lead, but Quarkus is now using less memory than Micronaut. So that was on 20 megs. Now let's jump up and let's say, oops, sorry, let's just change this here. Let's go and give each of them a maximum 5 gig heap. And let's see what happens. And this is where it gets pretty interesting. So what we can see now is that Micronaut boots up is using an RSS of 773 megs compared to Quarkus's 338. Now, I mean, I don't know why you'd ever want to give a maximum heap of 5 gigs, but you know, if you boot up in a JVM in an environment, you don't pass any parameters to it. It looks at how much physical memory you have available, and it ends up using, I think by default, something like a maximum heap of 25% of that or something. So if you start a JVM on a server with, like in this case on my laptop, 32 gigs of RAM, you can end up with Micronaut actually using a much higher RSS. It's not a big problem. I mean, the memory's there to be used, but just an interesting observation that Micronaut is using a lot more. Now let's have a look at why it is using a lot more. So even in this case, Quarkus's heap is larger than Micronaut's, but Micronaut has this 393 megs of other memory. I don't know what the other is. As I said, it kind of says in the documentation it's everything other than the other categories. But I'd be interested to find out what exactly Micronaut is doing to use 393 megs of native off-heap memory in this other section. Because that is what's making up this big difference. If it wasn't for this, Micronaut would have a lower RSS under these conditions. I mean, it is a bit of a contrived scenario. We've got a heap, we're saying, of 5 gigs, but at least a maximum heap of 5 gigs. But you can see that this is the net result is that Micronaut's sitting at a much higher RSS. Now what I want to do is another scenario is where we go and just set the min and max to the same. So what this does is it takes out any difference in how large the heap has grown, because the heap will be 128 megs on both of them. And then we can compare and see now any differences is coming from native memory utilization as opposed to how big the heap has grown. So here we will see that Quarkus uses quite a bit less memory than Micronaut. And this is almost like a scenario if you leave a JVM running for a long time. it's optimal to use the heap as opposed to garbage collecting. So if you left the JVM running for a few days, you would typically find that especially if you have a bit of spiky traffic or something, your heap would grow to the maximum, especially if your maximum is a fairly low figure like 128 megs. The heap is going to grow to that. So really what we're simulating is saying, let's just tell the heap that it must start off at the same as what its max is. And in fact, that's almost a best practice, because you're taking out any variability in your heap. You're getting your heap to a constant size when the JVM boots. Your garbage collector works within that, and your RSS will be a lot more stable from then on. And under these conditions, we've got 327 odd megs on Micronaut side versus 278 on Quarkus side, and Quarkus still leading a bit in terms of the throughput. Okay, so let's do a similar test like that, and let's have a look at with the J9 VM. We can see what kind of differences we observe here. So here again we're saying heaps must be static 128 megs. Let's have a look at the differences. And here we've got Quarkus, so 128, 128. Throughputs, let's wait for them to stabilize, see what happens. So the test runs through Micronaut first and then Quarkus. As the JITs are running, you'll see that the top result will always be a bit higher than the bottom until they stabilize. Interesting, the Quarkus quite a bit bigger on RSS right now, but as I had mentioned earlier with OpenJ9, things jump around a lot more because it will see what's what memory is reserved but uncommitted, reclaim it, give it back to the operating system, and you end up with, as things stabilize, your RSS drops quite a bit with OpenJ9. So now we're sitting at Quarkus 147 versus Micronaut 175. We can just leave it for one or two more runs, see what happens. About 150. 175, so still, and now things have stabilized. Quarkus sitting at about 25 odd megs lower than Micronaut. Okay, run a similar test. Let's really up the throughput here. Why not? Let's just go with 500 concurrency. Open J9, let's just see what happens. Interesting to see again, same as last one, when Quarkus first starts up, its RSS is quite high, and then OpenJ9 manages to claim back quite a bit more. You can see under this test whether what happens when they stabilize in terms of the RSS. So it's actually quite a big difference on throughput here. So Quarkus is sitting around 17 or so thousand requests per second higher than Micronaut, and Quarkus's native memory sitting around 20 odd megs lower than Micronaut. They both jump around a bit, but see on average Quarkus is definitely a bit lower as we run through the tests. Okay, let's do the same scenario, but let's run with both of them on event loop and see what happens. So now we're running very high throughput on event loop, so no context handover to worker pool, both running OpenJ9. So if you remember from previous scenarios where we ran both of them on event loop, Quarkus was quite a bit faster. We're seeing the same thing here. So we've got 69,000 versus 88,000. I think on hotspot, Quarkus was about 140, if I remember, about 140,000 requests per second. So this is growing as the JIT compiler kicks in. But we're seeing on the event loop side quite a big difference in quite a bigger difference in RSS. So Quarkus using 165 megs versus 200 on Micronaut now, with a fairly significant difference in throughput. Even bigger now the memory is 177 versus 235, 114 versus 84. So Quarkus is really looking good compared to Micronaut under this situation. Let's do a similar test with the hotspot JVM. Let's give each of them, say, 400 meg heap. You know, there's high concurrency going on. Let's give it a bit of a bigger heap, both of them on event loop. Let's see what happens. So this is probably going to be kind of the highest sort of throughput that we could expect. I don't know if 500 is. You may find that dropping that 500 a bit would actually get a slightly higher throughput. But let's just run this scenario and see what we get. So a bit meaningless to check right now while things are stabilizing, but we can kind of see that at 498 versus 374. Again, this is because of this other memory on Quarkus being on Micronaut being a bit higher. Whereas both of them, because the heap is 400 megs on both of them, it's this other figure that kicks in and really doesn't help Micronaut in terms of its RSS. Now it's RSS 506 versus 376, throughput of 88 versus, or not now 91 versus 100, so about a 10% higher throughput on Quarkus with a sure about 120 odd megs of RSS less. So this certainly makes Quarkus look quite a bit better in terms of throughput and RSS. Let's drop this from 500. Let's make the concurrency 100. See what we get. So similar observations. So sort of 100,000 versus 120,000, about 500 megs versus 410 megs. So still pretty much similar, slightly higher. So higher RSS on Micronaut and a higher throughput on Quarkus with lower RSS. But as I say, this is the event loop scenario, which is kind of all, you can't do any blocking or anything. The more realistic, I think, is to have an even playing field where both of them are using what was the setting? It was a IO. Sorry, what was the setting? So we had event loop, and then we've got if I say IO, I think. So IO will run with both of them doing a handover to a worker pool. So this again, even playing fields, both of them doing a context switch from event loop to worker pool. Concurrency of 100, no blocking, and seeing on Micronauts right now, Micronauts around 90,000 versus 77,000. 517 versus 489. Let's just wait for the JIT compilers to do their thing and for the results to level out a bit. So yeah, sitting around pretty similar. So the throughputs 92, 86, memory 522, 491. Okay, 89,000, 86,000, 524, 491. Oh, there's a big jump, so now Micronaut looking good, 90,000 versus 72. Maybe there was a GC happening, 90, 84, 526, 493. Okay. It's interesting how the slight changes in the setup in terms of your heap sizes can make a difference, because here, so Micronaut is ahead on throughput when we're doing both of them handing over from event loop to an executor pool. Higher RSS here than on Quarkus, but a higher throughput. But what we were observing earlier is if I just drop back to say 128 megs, let's just make both of them 128, 128. And now it's a concurrency of 100. Let's have a look what happens. I'm pretty sure that I was observing that Quarkus was getting a slightly higher throughput than Micronaut. But let's just have a look. So here, 89, 94. So yeah, I mean my memory served me right. Is that under these where both scenarios are handing over to an executor pool, was that with a slightly lower heap now. So before at 400 meg heap, Micronaut was above Quarkus on throughput, and now dropped the heap down to 128, and Quarkus is slightly ahead of Micronaut. Well, that test there was slightly lower, but I think it was maybe a GC or something, so they're sort of 89 versus 92. So generally seeing Quarkus slightly higher than Micronaut with a slightly, when the heap size is 128 versus 400. Let's go and set both of them. Let's give them like a 800 meg heap and see what happens. So 800 min and max, 100 concurrency, both of them handing over to a worker pool. Let's just wait for things to stabilize a bit. 91.86. I think we are seeing a similar similar pattern where with a higher heap, a larger heap, Micronaut slightly higher throughput than Quarkus, whereas with a smaller heap, Quarkus had a slightly higher throughput than Micronaut, 9185. So that kind of holds true again. Let's go to event loop and have a look at what happens there if we're not doing the handover with a 800 meg min and max heap. Again, we're seeing this big difference in terms of other. It's 131 megs used there versus 5 megs used here, which is really what's driving the much higher RSS on Micronaut than Quarkus. And we're seeing on our throughput, similar to what we had observed before, is that when Quarkus is not handing over to a worker pool, it is getting kind of this maybe 20% higher throughput than Micronaut. So we're observing that similar thing. So even with a larger heap size, both of them using event loop, Quarkus is about 20% higher throughput than Micronaut with low RSS. And I'd say it's fair to say that with a similar, also with a larger heap of around 800 megs, if both of them are using the a worker pool, then Micronaut is maybe getting a few percent higher throughput than Quarkus, whereas with the lower heaps, Quarkus is getting a slightly higher throughput than Micronaut. Let's try with say 150. I wonder where that kind of inflection point is, where they probably have a pretty similar throughput. Because we observed around 128 megs, Quarkus was faster. Around 200 megs and above, Micronaut was faster. Interesting to see at about 150 megs where the difference sits. So here we're seeing Micronaut a bit behind, now Micronaut ahead of Quarkus. '90 versus '92. '89.91. Wait for one more result to come through. 89.91. So it seems to stabilize. So around 150 meg heap, still Quarkus slightly faster than Micronaut. 88 versus 90. Let's give a heap of say 250, see what happens there. Wait for things to stabilize. It's 87, 84, 90, 84, 90, 85, 89, 84, 90, 84. So in just growing from 150 to 250, the tables turned from Quarkus being faster to Micronaut being faster. I say that, but now a test came through where Quarkus was faster. Let's just see, definitely. So Micronaut 91 versus 85. So under slightly higher, as soon as you start getting the heap over sort of 200 megs or so, then the tables turn. Micronaut gets a higher throughput than Quarkus. Um, let's try again with, say, a 5 gig min and max. So this is both of them starting with pretty big heaps, and let's see what happens now. So 89, 84s, I think we're seeing a very similar results. Micronaut higher throughput than Quarkus with higher RSS with larger heap sizes. Let's just for interest sakes try with the min heap of 0, so the heaps can grow up to 5 gigs, but don't start at 5 gigs, and let's have a look at what happens here. Memory, so Micronaut 762 versus 492, requests per second 87, 84,000. 88, 86. So let's try one last scenario. Let's try with 20, or let's try 50. Let's put both to 128. Let's set this one to, we can say it and start at 0. So 50 throughput, max heap of 128. Or let's go 250. 250. Hotspot, both handing over to a worker pool. So RSS 310, 347, because Quarkus jumps up here with the 179 megs of the heap used, whereas Micronaut's a lot more frugal on the initial heap, but a higher other memory used. So we're sitting at 303 versus 355. Transactions per second 85, here 86, 84. Wait for another set of request results to come through. 86, 84, 304, 352. So here we have a scenario, Micronaut, higher throughput with lower RSS than Quarkus's throughput. Quarkus, well, right now Quarkus slightly higher, but let's just wait for another result. 85, 83, I think that's kind of more typical what we're seeing. So Micronaut higher throughput with lower RSS than Quarkus. And if we simulate a heap which is kind of stabilized to using its maximum, then we'll end up most probably observing Quarkus with a lower heap than Micronaut, with a lower RSS than Micronaut. 325, 317, because of this other memory. So I'd really be interested to see from the Micronaut team what's being used, because I certainly think if they could lower this other memory utilization here, it could save quite a bit on RSS and certainly get down to Quarkus's RSS at least. Looking at throughput, 87, 77. 7681. So Micronaut, higher throughput, higher RSS. Quarkus, lower throughput, lower RSS. Okay, and let's run one more scenario. 25 megs fixed, 50 throughput. Let's see what happens. So Micronaut sitting, so now we're at 179 megs versus 164, 62,000 requests per second versus 71. So interesting how we're seeing that same, we're observing that same same behavior of Micronaut's throughput um, slowing down quite a bit more when it's given a smaller heap. Quarkus being able to maintain a higher throughput even with a lower heap, which I think does talk to Quarkus being a bit more efficient in terms of its heap usage. If it can be have a higher throughput with a lower heap, but then as we've seen, if you start getting to a heap of over say 150, 200 megs, then Micronaut makes up the difference and ends up getting a slightly higher throughput than Quarkus, but with a higher RSS. So now we've got RSS 187, 171, 68 versus 77, 67, 75. Let's run a scenario with 250 megs and a 2 millisecond sleep with a concurrency of 100, both of them handing over to worker pools. So this is kind of a realistic high load scenario, doing a bit of blocking database work. Maybe do some few database calls, kind of blocks for 2 milliseconds, 100 concurrent requests, and a heap of 250 megs min and max. So RSS wise 425 versus 377, throughputs both sitting around 45,000 transactions per second. You know, as you start blocking, then you end up with smaller differences in throughput, because you're not really just measuring the raw performance of thread context handovers and that sort of thing. You're more compensating for doing some real life work. So the differences end up becoming pretty minimal. RSS about 50 megs higher on Micronaut than Quarkus. 45 versus almost 45. I think these jump around a bit as the results. 45, 45. So not much difference in terms of throughput, just a slightly higher RSS on the Micronaut side. So that's my ramblings. Took a while. Interesting observations. I think it's, as you can see, comparing things apples to apples does make a bit of a difference. I think both of them are great frameworks. As I say, I've worked with both frameworks. I think it is worth, though, just if you're going to be comparing things, I think it's right to mention whether you're working with event loop threads versus handing over to worker pools. It's more real world to hand over to a worker pool, because typically your code is going to be doing some blocking work. You don't want to end up with a scenario where you almost kill your whole container, because as I said, if you go back to default mode and we run like this, where Quarkus ends up handing over to worker pools, but Micronaut doesn't, you'll see that it has a huge impact on Micronaut in terms of your throughput. So it's not really fair to be doing comparisons where one is using only event loop and the other one is handing over, because you can make those comparisons look really bad as well by just adding in a bit of real world blocking and seeing the impact. So that's why I think this test of having one doing using pure event loop and the other one handing over to a worker pool is a bit of apples to oranges, and by comparing them both the same, maybe to summarize, what I found is that if both of them are using pure event loop processing, then Quarkus ends up using a lower RSS and gets maybe about a 20% higher throughput than Micronaut. And if you are using both of them handing over to a worker pool, then on heaps, say lower than around 150 megs, um, Quarkus has a higher throughput than Micronaut. Heaps above that, Micronaut has a higher throughput than Quarkus, but in both cases, Quarkus has a lower RSS than Micronaut. And I'm observing that low RSS is due to Micronaut having this larger other native memory used up, which counts against it in terms of the total RSS size. So that's it. That's my summary, and I will paste a link to all of the source and my little monitor script. I'll put it on GitHub, and people are free to run through the test themselves, see what they observe, and yeah, thanks for listening.